Hi, everyone. Welcome back to another Talk Math with Your Friends. And today is a special one for me. Our speakers today are undergraduate researchers co-advised by myself, Tien of MSU-Billings, and Dr. Laura Scull of Fort Lewis College. This work is funded by the good people at Kernel and the NSF. And so this work revolves around cross-homotopy graphs. So please join me in welcoming Alexis Stahl and Ralph Studer of MSUB, and Simon Hobbs, Daniel Lewis, and Kai Martino of Fort Lewis College.
Hi, everyone. So our branch of this project at MSUB was we titled it Group Relationships Between Graphs and Their Unique Stiff Subgraphs. And so we started off by just defining a graph, which is a set of vertices and edges.
Then we define a homomorphism, which is if it's a homomorphism, edges are preserved. So you can see in our example, we send W to V, and because V and X already have an edge, sending W to V preserves that edge.
So next we look at a spider pair, and this is when two homomorphisms differ by at most one vertex. So we can see here that row of V is U, V is sent to U.
And then we have another example here where the two graphs only differ at V2.
So we say that two homomorphisms are homotopic if there exists a sequence of spider moves in between them. So you can see in this example that the antennae coming off of G are all just folded into Y. And so the identity of G is homotopic to the folded antennas on the right.
Then we defined a spider web, which is where the vertices are homomorphisms from G to H, and there's an edge between them if two homomorphisms, if they are a spider pair. And then we looked at spider nests, which was a spider web from a graph to itself. So we have an example here of G and the spider nest of G. And you can see if you folded C to A, you'd get ABA, and you can see that is in the spider nest of G, and so that's a homomorphism that's in there. And so you can find all homomorphisms in the spider nest.
So next, a fold is just simply a single vertex moved to another. And we use row to express a series of folds. So we have the same example where row of V is U.
So given our folded row, we get this iota such that these facts are true, where row iota is homotopic to the identity of H, and iota row is homotopic to the identity of G. And then we define a stiff graph, as there is no more folds available to do. You can't do any more folds.
So then next, from the stiff graph, we define the pleat as the unique stiff subgraph of G. And we can see in this example that the two antennae are folded in, and that's the action row. And then iota is the inclusion map of pleat G back into G.
So next we define null, and it is automorphisms of G that are homotopic to the identity. So here we have our G, and we wrote out the automorphisms of G. And now we wanted you guys to see if you could figure out or say what the null of this graph G would be.
I don't remember all of the definitions, but if you can achieve one of the rotations, then I'm going to guess it's the rotation subgroup.
So just throwing out the first. So first we have the identity of G, and then if we switch C and A, that's one of the first ones. So we can't, we have to maintain the edges. So rotation would work if we go 2 to the left. So we also have to maintain the parities of the vertices original position.
Yeah, so there are homotopic or to the identity if you can do one spider move at a time. So like he said on the first one, you can move A to C and then C to A. And then on our second one where you switch B and D, you can move B to D and D to B. And then the last one is doing both of them. So they're all just a series of spider moves between the automorphism and the identity.
So one of our first lemmas was when we compose a homomorphism with a series of spider moves, the spider moves are preserved when they are composed together. So F1 is homotopic to FM, and this implies that F1 composed with phi is homotopic to FM composed with phi.
And then we did the post composition to show that that also preserves the spider pairs. Therefore, if F1 and FM are homotopic, then F1 composed with phi is still homotopic to FM composed with phi. And we use these results a lot in our next stuff.
So next we proved that null G forms a subgroup of aught G. And if we look below, we can see that for closure, we have alpha is homotopic to the identity as well as beta. And then alpha composed with beta is homotopic to the identity composed with beta. And thus alpha composed with beta is homotopic to beta. And then for the inverse, we can see that alpha composed with alpha inverse is homotopic to the identity composed with alpha inverse, and thus the identity is homotopic to alpha inverse.
So then we wanted to prove that it was a normal subgroup. So if alpha is in the null G, we know it's homotopic to the identity. And using those composition lemmas, we know we can compose it with X inverse and it's still homotopic. And then we can compose it again with X and get that X alpha X inverse is homotopic to the identity.
So we learned from there that rho destroys homotopies as well as aught G mod null G destroys homotopies. And this led to our big question of, is there a relationship between aught G mod null G and aught pleat G? And the reason rho destroys homotopies, just to brush back over that, is because all folds are eliminated by definition of the stiff subgraph. And then aught G mod null G just factors aught G with null G, which also destroys the homotopies.
So then we looked at if do this mapping if we get an automorphism of SNG. So we have our graph G on the left, and then we have the spider nest. It's not the full spider nest though. We only looking at the automorphisms. There are homomorphisms in there. It would just be a really big graph if we included them, and we weren't looking at them anyway. So if we were to like compose it, let's say phi was CD, switching C and D, and we compose each of these vertices of the spider nest. So we get identity composed with CD gives you CD. AB composed with CD gives you ABCD. ABCD composed with CD gives you AB, and CD composed with CD gives you the identity. So you can see that no matter, they all are still in the automorphisms, and you actually get all 4 elements again. And the same thing happens in the right-hand component as well.
So next we prove that if A prime is in pleat G, then A prime is an isolated vertex in the spider nest of pleat G. And we can see from this example that pleat G has no spider moves available, and thus any other component in the spider nest is going to be an automorphism that is not spiderable or can't be spidered to.
So then we want or prove that psi gamma is a group homomorphism. So, and this is a proof in essence. There's a lot of pieces that we didn't include in the presentation that are in our paper, but it would have been really long if we included them. So psi gamma A, psi gamma B would equal rho A iota, rho B iota by definition. And that is homotopic to rho A, the identity of G, B iota, since iota rho is homotopic to identity of G, which then we get equals rho AB iota, which equals psi gamma AB. Therefore, we get that psi gamma A, psi gamma B is homotopic to psi gamma AB. And since all the automorphisms of spider nest pleat G are isolated vertex, they must be equal. Therefore, it is a group homomorphism.
So here we have an animation to kind of get a better feel of what that group homomorphism looks like. The domain here is pleat G. And we can see when pleat G is mapped back into G, it is just the image of pleat G. So here we have iota composed with AB with the reflection composed with rho. And we can see that's equal to psi of the AB composed with the reflection.
Here, Alexis, could you start the animation back from the beginning? You hit jump.
Yeah, I think I hit the wrong button. Let's try this again. There we go.
Okay.
Sorry about that.
There we have iota sending the image of pleat G back into G. And then composed with AB. And then we can see rho sends that back to the identity of pleat G in the spider nest of pleat G. And then iota maps the image back into G. And then we do the reflection that trades X or sends X to Z and Z to X. And then we can see when rho sends that back into the pleat, we are now in the component that contains XZ rather than the identity. So by definition, this is our psi gamma. And this shows that psi gamma of AB composed with the reflection is equal to XZ in the spider nest of pleat G.
So then we're gonna do example where we do AB and the reflection first before we send it back. So here you can see we did rho AB or RAB, and then from there it'll send it to XZ, which is what we got when we did them individually, did row AB iota and then row R iota. So therefore we get that they are equal. Okay, so then one of our theorems was that null G is equal to the kernel of psi gamma. And then our answer to our big question that we asked was, is that aught G mod null G is isomorphic to a subgroup of aught pli G. So then we have this example here showing that null G equals the kernel of psi gamma. So we have our graph that we've been using, and we have the spider nest of it, and then we have our pleat, and then the spider nest of the pleat. And we know that all of the automorphisms that are homotopic to identity are the null. And so then we can see the blue circle component would be all of our null of G, because they're all the automorphisms that are homotopic to the identity. So then we can see that they all get mapped to the spider nest pleat G and the identity. So that the little blue circle. And since they all get sent to that component, that makes, or to the identity, that makes a kernel as well.
So here's another pretty simple example. We can see that the spider nest of G is just those automorphisms along with the homomorphisms that aren't included, but we can see that each of those again is mapped to the identity of pleat G and its spider nest. And then anything composed with the reflection is mapped to the other component in the spider nest.
So we have one last example, and this one in our spider nest, we actually included the homomorphisms, but again, we still weren't looking at them. We just included them in the spider nest. So you can see again, on the left hand, we have the automorphism that is spiderable AC, and that component maps to the identity. And therefore, again, the null is equal to the kernel. That's because the blue maps to the blue.
So that was pretty much it for our portion of this research. And we had quite a few people that this wouldn't have been possible without. And so we want to thank everybody in here and for inviting us to do this. And thanks for watching.
Thank you. Dan, you're in terms of time. Do we want to move on?
Do we have time for a question or two, Tien?
I think that's up to for those people.
Okay,
but-
yeah.
Yeah, we have time for a minute or two of questions before we take over.
Okay.
So Paul asked, is it a coincidence that each connected component of the spider nest gets mapped to the same element of the spider nest of the pleat?
Oh, sorry, could you repeat that?
It's in the chat if you want to read it, but is it a coincidence that each connected component of the spider nest gets mapped to the same element of the spider nest of the pleat?
No, it is
Right.
not a coincidence. Again, that's actually one of the proofs we did in our paper, but unfortunately it was one of them we didn't put in here, but it is not a coincidence. It does happen for a reason.
Yeah, so what they forgot to mention, or well, I'll mention it instead rather, is that psi, when unrestricted to automorphisms, is a graph homomorphism from spider nests to spider nests. And so we were going back and forth a lot in thinking of these things as both group elements, as like automorphisms, and also as vertices of graphs. And it was combining those things that they were able to do all the cool stuff that they did.
Sweet, so meta.
Cool. Thanks for that.
Excellent, thank you. Let's shift to our other group. Thank you.
All right, hi, I'm Cinnamon. I'm here with Dan and Kai from Fort Lewis. And since they did such a great job of looking at spider nests, which are spider webs where your domain and codomain are the same as each other, we're going to introduce you to the rest of spider webs where there are no automorphisms because your domain and codomain are different from one another. So just for simplicity, we're going to stick to finite connected graphs with no loops, like the ones on this slide. I do want to show you, this is a notation that we'll use in our proofs to denote when there is an edge between two vertices. And we're going to talk to you a lot about bipartite graphs. So briefly, a bipartite graph is a graph where you can partition the vertices with two colors, such that, for example, no pink is ever having an edge to another pink, no blue ever has an edge to another blue. And what ends up happening is that all vertices of the same color are connected by an even length walk, whereas vertices of the opposite color are always connected by an odd length walk, and only by an odd length walk. I do want to highlight for a star graph, like the one I have in the center, one of those partitions is always just the center vertex, and the peripheral vertices make up the other partition. So let's look at what a graph homomorphism looks like between two graphs that are not the same. I'm going to map my cycle graph into my star graph, like so. This is just one option for a homomorphism, and all a homomorphism has to do is preserve edges. So you can check, for instance, just as 0 had an edge to 1 and an edge to 5 in my domain, the image of 0 still has an edge to the image of 1 and to the image of 5, and so forth. So if I want to do a spider move, what I'm going to do is I'm going to change the image of one vertex. So I'm going to take the image of 5, and I'm going to snuggle it up there with the image of 1. And we just have to make sure that this is still a graph homomorphism for it to actually be a spider move. The only vertex I moved the image of was 5. It had an edge to 0 and an edge to 4. And in fact, my new image of 5 still has edges to the images of 0 and 4. So I'm good to go. This is a legitimate spider move. Just for the sake of simplicity, to keep the diagrams clean, sometimes I will represent them like so. All right, so you might have looked at that and said, somehow I managed to map all of my vertices of one color to a single color in the codomain, and all my vertices of the other color to the other color in the codomain. Like here I have pinks going to teal and blues going to purple. And that is not a coincidence. I can choose whether I send pink to teal and blue to purple or vice versa, but I can't mix them up. And that is because homomorphisms preserve edges, and a walk is a series of edges. And so if the walk 0 to 1 to 2 to 3 to 4 was a length 4 walk in my domain, the images of 0 to 1 to 2 back to 3 to 4 are still a walk in my codomain. And since in a bipartite graph, vertices of the same color are separated only by even length walks, and I've preserved my even length walk, and my codomain is bipartite as well, the only option is that I've mapped all of my blues only to purples. So I want to look at what happens after we do a homomorphism and then we start moving our images around the spider moves. So for any pair of graphs, I'm going to convince you that when you do a spider move, there is a length 2 walk in the codomain between where your image was and where the image of the vertex that you moved ended up. So I'm going to take an arbitrary vertex x from my domain, and we'll stipulate that's the one I'm going to move with my spider move. Now, that vertex x had to be connected to something else in the domain, and since homomorphisms preserve edges, their images were connected in the codomain. When I move my image of x, it's the only one I move. I can't move the image of y, and so it will remain the same, and it still has to be connected to the new image because it must preserve edges. So there's my link to walk. And the upshot of this for bipartite graphs is since I know that every time I do a spider move, the image that I move moves by a length 2 walk, I can do as many spider moves as I want. I can move my entire image to somewhere else on the graph. And I know that where my image started and where it ended up will always be connected by an even length walk. And that means that at no point has the color that my vertex mapped to changed if my codomain was bipartite. So let's look at how we build a spider web between two graphs that are not identical. What I'm going to do here, I'm going to take all of the pink vertices from my bipartite circle graph, and I'm going to map them into the center of this bipartite star graph. And that means I'm going to distribute the blue vertices between the two outer edges. Now, because every blue vertex, if it has an edge, that edge is always to pink, and I mapped all my pinks to the center, and the center has edges to both my outside vertices, I can put any blue vertex anywhere I want on the outside, and it will be a legitimate homomorphism. So I've got 3 blue vertices. I have 2 places a piece I can put them. That should give me 8 homomorphisms. These are my 8 homomorphisms. If you look at the way I've arranged this, as you go from left to right across the top, the first one is a spider move to the next one, because all I've moved is the image of 5. And that has a spider move to the one that follows, because all I've moved is the image of 3. That's a spider move to the next, and the last is a spider move all the way back to the first one. I've done the same thing on the bottom, set them up so it's one spider move to the next, going across the bottom, and then back to the first. Also, if you look at the top left and the one below it, all that's changed is the image of 1, so those are a spider move as well. And in fact, all of these from top to bottom are a spider move. Now, in a spider web, each one of these maps will be represented by a single vertex, and there will be an edge between vertices if those 2 maps are a spider move. And so if you wrap all of these around, you are going to get a cube in your spider web. This is just half my spider web, because remember, I could have made the opposite choice with my bipartitions. I could have mapped all of my blue vertices to the center and pinks to the outside. That would have given me an identical cube. And because we've established that spider moves always move an image by a length 2 walk, there's no way to spider move my way out of the bipartition, so there won't be any edges between these 2 cubes. So we wrote some code that will take any domain and codomain that you give it, and it will show you what your spider web is going to look like. And I just want to show you some of my favorites. These come in so many different amazing shapes and sizes. Here's a cute little Christmas wreath. Here's some little Christmas toys. And this I want to point out because these are both bipartite graphs in my domain and codomain, but I got more than 2 components in my spider web. That is a phenomenon you see a lot with cycles. They propagate web components like crazy. Some graphs I figured out how to look at a pair of graphs and tell you how many components you will have in your spider web. Some of them I'm still working on, but there's one that's really easy to explain. And that is if you take any bipartite graph at all and you map it into a star, you will always get exactly 2 components, no more, no less. And I think you're probably convinced by some of the bipartitions that we've seen that it will be at least 2 components. But what I want to convince you of is that unlike what you saw with the cycles on the previous slide, there's no sneaky way that I'm going to have more than 2 components in my spider web. So what I'm going to do, I'm going to take an arbitrary bipartite graph, going to color it pink and blue. I'm going to map all my blues into the center of the star. And I want to convince you that every possible homomorphism that does this, which then maps pinks to the outside of the star, will be homotopic by a series of spider moves to each other, so that I will only get 1 component out of this choice. So I'm going to pick a favorite vertex on the outside of the star. And then I'm going to just say this is an arbitrary homomorphism, mapped my blues to center, mapped all my pinks to somewhere on the outside. I'm going to pick another vertex. I'm going to look at it and say, did a pink vertex map here? If so, I know that all of its edges are going to be two blues in the domain, because the domain is bipartite. All of those map to the center. The center has edges to all of my peripheral vertices. So I can spider move that vertex anywhere I want. And I'm going to spider move it to my favorite vertex. And then if there's any more vertices that mapped to the same place, I'm going to do the same thing with them until there are no more pink vertices mapped there. And I'm just going to go around my web, and I'm going to keep doing this until I've spider moved every pink vertex to be mapped to the same place. And since all blues only have edges to pinks and all pinks only have edges to blues, I know for sure this is a homomorphism. And by a series of spider moves, everything else that mapped pinks to the outside will be connected in the web to this. And then the other component comes from mapping pink to the center instead. So depending on your bipartite graph and the size of your star, you will get all kinds of different shapes and sizes and structure within your two components of your spider web. And that is what Kai is going to tell you all about.
Okay, hi, I'm Kai, and so you saw Cinnamon's slide where she had 8 different maps and she connected them accordingly, and they formed a cube. That was super cool. And what I studied was the structures of the web, such as that one. So what we're building towards is let G be a bipartite graph with bipartition A and B, and if we map that into any star graph, we will have 2 of these things called Hamming graphs. So definitions. A star graph is a graph that looks like a star. It will have a center, and the star graph n will have n-1 legs connected to it on the outside. Cube graphs are defined by Hamming distance. A Hamming distance is the number of differing digits in 2 binary strings. They are Hamming distance 1 if they differ at a single spot in the string. So a cube graph Q of n has all the possible length n binary strings, and they will be connected if they differ at 1 digit, and we will have cube graphs in that case. So first, I'd like to show that the web, as we map Sn into S3, is just a cube graph n-1 and K2. K2 being just 2 vertices and an edge connecting them. As Cinnamon showed us, there will be 2 components to this web, one corresponding from the center mapping to the center, and the other corresponding from the center not mapping to the center. We'll break it down into 2 cases. So first, in the center not to center component, all of the legs in the domain get mapped to the center of the codomain. The center of the domain can move between any leg in the codomain. In this particular case, there are 2 places it can be, and you can see how the center moves back and forth. They will be connected by a spider move, which means we have 2 vertices and 1 edge, K2. Now for the center to center component, the center obviously goes to the center, but then we will have all the legs get mapped to the legs. We can assign a 0 and a 1 to each leg in the codomain. And if we look at our left case example, we can assign binary strings to each map. We see that 1 gets sent to 0, 2 goes to 0, 3 to 1, 4 to 1. And so we can assign a binary string 0, 0, 1, 1. These binary strings, they differ by a single digit, which means they are Hamming distance 1. Also equivalently, we can see how the 3 is moving back and forth, which means they are a spider move. Spider moves correspond Hamming distance 1, so our web will just be cube of n-1. We have length n-1 binary strings. So in summary, you can see how the domain S of n corresponds to the size Q of n-1. So first step of generalization. Hamming distance can be defined by any k-ary string as opposed to binary as we did earlier. K-ary is as in binary, ternary, ... k-ary. A Hamming graph, h of nk, is a graph with vertices of k-ary, length, and strings, connected if they are Hamming distance 1 away from each other. So the second thing we're going to be showing is that the web from S of n into S of k, so any arbitrary stars, will just be a Hamming graph and a complete graph. Complete graph k of k-1 being k-1 vertices, any pair is connected by an edge. Dan will be talking about these much more later. So the proof will be the same thing. We'll split it into 2 cases, center to center and center not to center. So for the center, not the center component, again, all the legs in the domain will be sent to the center of the codomain, and the center of the domain will be sent to a leg in the codomain. In our case, we have k-1 spots it can be, and it can spider move to any other spot, which means we have k-1 vertices, and any pair will be connected by a spider move or an edge. For the center to center component, instead of assigning binary strings, now we can assign k-1 array strings, k-1 array strings of length n-1. So in our example, I'll look at the left case, we have 1 goes to 3, 2 goes to 2, and 3 goes to 0. So we have the k-1 array string 3, 2, 0. So we have the Hamming graph h of n-1, k-1. And in here, sort of a list of examples where you can see how the s of n and s of k corresponds to Hamming graph h of n-1, k-1. Our final generalization is that we will let G be bipartite with bipartitions A and B, and then we'll map that into any star graph. This will be 2 Hamming graphs where they each correspond to the size of our bipartitions of G. So in terms of our proof method, we will first map G into G prime, which will be a star graph. G prime will be constructed so that all of these green vertices get mapped to the center, and all of the red vertices get mapped to a leg. And this will be done injectively. So there will be as many red vertices as red vertices in G and S6 in our case. Now we will compare the original web that we were looking for, and we will compare that to the new web, G prime into SK. We can find our web that we're looking for from this relationship. Okay, so mapping G into G prime. We'll define phi from G into G prime, where the bipartition B gets sent to the center and bipartition A gets sent to what I'm calling F. F is just all the non-center vertices in G prime. Phi will be a surjective graph homomorphism, and it's also bijective between the bipartitions A and F. So let W, this is for shorthand, let W be the web from G to SK, but we're focusing on the bipartition B getting sent to the center component, and let W prime be the web from G prime into SK, but we're focusing on the center gets sent to center component. So we'll define phi star from W prime into W as phi star V equals V phi, V being an arbitrary vertex in W prime. Now, since W prime is a web, keep in mind that a vertex V from it is just a map itself. V phi is a composition of maps, as we showed that phi is also a map. And this map will be in the web W, since V phi goes from G into SK, as you can see from our little diagram here. So we'll show that phi star is a homomorphism that is also injective and surjective, which means it is a isomorphism. So let V and W inside W prime be given. If they're connected, that means they differ by a single output as maps. Let that output be AN prime, let's say. Note that this output cannot be the center C, because there's only one center. We can't send a center to multiple places and stuff like that. So because phi is bijective between the bipartitions A and F, there is a unique AN such that phi of AN maps to AN prime. And it follows, we see from the bottom sort of non-equation we have here, that V phi and W phi differ at that single vertex AN. So by a similar proving method, using bijectivity of phi between A and F again, we see that every other output of V phi and W phi will be indeed equal. So V phi and W phi differ by a single output only, which means that they are connected by a spider move, they are connected in the web. So phi star preserves vertex connectedness, it preserves edges, which means it is a graph homomorphism. Phi star is also an isomorphism. We can show this by seeing it's injective and surjective, the proof outline is being shown right here. And we now have an isomorphism, phi star, between W prime and W. We have this chain of isomorphisms that you can see in the first bullet point. So the first isomorphism there is being given by phi star, and the second isomorphism is being given by the star to star stuff that we did in our second chapter, we can call it, as we did earlier. So we have that the connected component of the web GSK, where the bipartition B gets sent to the center, is just a Hamming graph that depends on the size of A. Similarly, the component where the bipartition A gets sent to the center is isomorphic to just a Hamming graph where the size depends on the bipartition B. Now, since our web has two components, we've found both of them, we can conclude that the web of any bipartite graph G into a star graph is just two Hamming graphs where each of their sizes depends on the size of the bipartition of G. Hopefully this gives a little more context as to what was going on, where Cinnamon did her thing there, and that's it for me. Let's go to Dan.
Hello, I'm Dan. I looked at the complete graphs, which look like this. They're denoted with KN. They were already mentioned by Kai. It's just n vertices that are each connected by an edge with no loops. Pretty straightforward. Here's some examples. And so I was looking at the spider web for a smaller complete graph into a larger complete graph. That is Kn into Km, where n must strictly be less than m. For instance, here's an example for K3 into K4. And so for the spider web, you'll recall that each vertex is a map from K3 into K4, and each edge represents a spider move between those maps. So the question I set out to answer is, if we pick a vertex in one of these spider webs, how many vertices are distance 3 away from it? Distance 4? Distance D in general? And by distance, what I mean is the length of the shortest walk. You'll recall walks from when Cinnamon was talking. So just the length of the shortest walk is what I mean by distance. And because the complete graphs are so regular and symmetric, it's reasonable to expect that our choice of vertex won't much matter here. Pay attention to the notation at the bottom of the screen. That will come back up, big D, little d of NM. That is saying for the spider web of Kn into Km, pick a vertex, how many vertices are distance little d away. So for the sake of concreteness, let's set some real values here. Let's say n equals 4 and m equals 7, and 4 is less than 7, so we're good. And we can represent each of the vertices in the spider web like this. Each one of these is a homomorphism, and so each of these would be a vertex in the spider web. And note that we can map this however we want. As long as we do it injectively, we can put these vertices anywhere we like and still have a legitimate match homomorphism. So we can represent a single vertex with a diagram like this. But those lines are really just getting in the way and not adding much, so we can go ahead and get rid of those, represent the vertex like this. That means that a spider move between the diagrams is going to look like this. Two diagrams where the letters are placed the same everywhere except at one place. Here they agree at A, E, and C, but disagree at B. And that makes these diagrams a spider move apart. Further, we can use this to compare two vertices. For instance, here we have one vertice, a red vertice represented by red letters, and a blue vertice. So now we've reformulated the question. We have two equivalent formulations for distance in our spider web. And this works because the spider moves in the diagram correspond to edges in the spider web. So let's take an example. How many spider moves do we need to get these to agree? Well, B is in the way of A, so we can move that into place first. And then now we're open to put A where it goes. C and D are mutually blocking each other, so we got to move one of them out of the way. So let's get D out of there. Now we're open to move C into place, and finally, we can put D where it goes. And so overall, that took us 5 moves, so we know that these vertices are distance 5 apart in the spider web. So now we've essentially turned this question about graphs into a question about our diagrams. Instead of just asking how many vertices are some distance away, we can ask how many ways can we place the blue letters so it'll take that many moves spider moves to get the diagrams to agree again. So I broke this up into two primary cases, identical images and different images. Note that by identical images, I don't mean identical maps, just that the maps have all the same vertices. And for case one, it only depends on the values of n and d. It's a really interesting story about integer partitions that I don't have time to tell you all right now. It does end up being non-trivial and will be kind of like this. But right now, what I'm going to tell you more about is case two. So how can we place the blue letters so that our images disagree properly while maintaining the correct distance between the vertices in the spider web? So we're shifting from the main question of distance now to a sub-question about how to make our images disagree. So we'll have k be the number of positions we disagree at. What do we know about k? Well, we're in case two, so it's got to be at least one. Also, it's always going to take at least k moves to move our blue pieces back. In this example, we've moved 3 blue letters off of our image, so it's going to take at least 3 moves to get them to agree. So d can't be any less than k, or in other words, k has to be less than. Likewise, we only have k or m minus n, in this case 3 empty spots to move on to. So k can't be bigger than 3. You only have that many slots to move on to. And of course, k can't be bigger than n because you only have n letters to move, so we can't move more than that. Okay, so let's suppose that some value for k is given to us now that we know the bounds on it. And again, k is the number of places where our images are differing. So we have k blue letters that we want to place in our diagram so the images don't differ. Well, in this case, we have 4 letters to choose from. So for which letters we're moving, that'll be 4 choose k. And then we have 3 slots we can put them in. So choosing the slots, that'll be 3 choose k. And then we have the options for how to arrange the letters that we put down. So that will be k factorial. All in all, we have, this is how many ways we can place the k blue letters in our diagram. But what if d is bigger than k? I mean, it's going to take at least k moves to get back, but we're looking for a distance of d. Take the case where d equals 4 and k equals 2, and say that we've placed our 2 letters like this already. Well, that's going to take 2 moves to get back, but we need for it to take 4 moves to get back. So what now? We got to place a and d. We can't place them, our k was 2, we already have 2 outside of our red image, so we got to place them within the red image. And b and c are essentially not a factor anymore. But we do have to place a and d so that it takes 2 spider moves to get us to get them fixed. So that then when you add that to the 2 from our k, you get the 4 that we're aiming for. So do these constraints seem familiar? We can reduce the problem. We found a smaller version of the problem in the problem. And we can use the smaller version to solve the problem. And so that's really cool, because look, we just got these 4 vertices we're worried about, and we're just worried about mapping 2 letters onto them so that we get the correct distance. This is the same as asking for d sub 2 of 2, 4. In general, it's going to be the same as asking for d sub d minus k of n minus k n. It's recursive. We're using a smaller version of our problem. So in the end, we did find, I found a formula for what I was looking for. It's like this. Notice that we have case 1 there. And then in case 2, we have the summation where every term is getting hit by a d sub t bn, where an answer to this problem from a smaller iteration. So I'll let y'all look at that in just a second. Okay. So I have a whole outline of a combinatorial argument, part of which you just heard. Besides that, I checked computationally for all n less than equal to 10 and all the other relevant values and found no mistakes. So formula seems really good. And then just a quick review. So I was answering this question, for some distance, how many vertices are that distance away in the spider web? I broke it up into two cases. And I showed you the formula for case one, even though I didn't have time to prove it. For case two, we bounded the number of places our images could differ at. We used a standard counting argument to work that out. And then to account for any more distance that we needed, we used this really cool recursive counting technique to get us the rest of the way there. Besides this, I did a significant amount of code. I generated spider webs. I made an algorithm that can generate spider webs by breaking down their domain in various ways. And I explored Cartesian products and automorphism groups and such. Yeah, and so now I'm going to hand it back over to Cinnamon to finish up.
All right, so I want to give you just a tiny taste of one of the directions that we're going with this next. So I mentioned that a bipartite graph to a star graph gives you two components. In fact, if I have two bipartite graphs and neither one of them, they just can't both have cycles in them, and then I will get two components. If they're both cycles, it's a little bit more complicated, but I have sorted out how many components to expect. Most of them come from just wrapping one cycle around the other. What I have not been able to sort out yet is if I have more than one cycle in my codomain, how many components should I expect? If you give me a specific codomain, I can figure it out, but coming up with some kind of generalized understanding of how many components there should be has turned out to be a bit more slippery than I anticipated. I don't even know if a generalized formula exists, but if it does, the most promising approach that I have found so far has been to look at groupoids of all the possible walks in the domain and all the possible walks in the codomain and examine the relationships between those groupoids and the connected components in the web. And I think that that's interesting, and that's one of the directions we're going with next. We would like to give a huge thank you to Kerm and via them, the NSF, for providing the funding that made us be able to take the time to do this project. Thank you to Fort Lewis for being so amazing at sponsoring undergraduate research in all subjects. It's not on this slide, but I want to give a huge thank you to Laura for believing in us and for mentoring us. And I am sure that Dr. Chi has also been absolutely fabulous to his students looking at their research. And we really want to thank you guys at Talk Math with Your Friends for opening your doors to us, letting us come in here as undergraduates, giving us a place we could actually talk about our research to other mathematicians, especially during COVID when there weren't any conferences for us to go to. Thank you so much.
Excellent job, everyone. If you want to unmute and clap out loud, that would be great. We have a couple of minutes for questions if anyone would like to ask one.
I was wondering, are these definitions
Yeah.
original with your team, or is this something that's an active area of research in other areas?
So we so the idea of the definition of this type of homotopy precedes me and Laura's work together, but we proved a result in our first paper on this subject that for finite graphs at least, any two homomorphisms, if they're cross homotopic, there exists the spider move. So we defined this idea of spider move that wasn't the original definition of homotopic, but it's a much easier to digest one, and it unlocks a lot of the behavior of what it means to be cross homotopic. And so that, and it's also, as you can see, something that makes a lot of these problems more tractable. Yeah.
Where are you going with this research? Are you going to publish anything?
Students, please, yes.
Speaking for Fort Lewis College, yes, I think we're definitely shooting for trying to, but we haven't quite sorted out the details.
I'd like to as well, but it's, you know, my students were seniors. They finals were last week, so I know they're in the midst of like the next phase of their life currently. So I would like to, but it's really a matter of modulo time, right? Modulo, like real life.
Great. Well, let's do our little wrap up announcement. So everyone is invited back next week. Carol Jacoby is going to be talking about the liar's paradox and the foundation of mathematics. Carol is here. Carol, would you like to give us a 30-second preview?
Sure. This isn't anything about my research. It's just something I find fascinating. The liar's paradox, which seems like just a silly paradox, but it really has implications in the foundations of mathematics. So that's what I'm going to be talking about. Mind-blowing stuff.
All right, one more time, please unmute and join me in thanking our excellent student speakers today and their really impressive research.
Woohoo!